Hello! In this video, we are going to prove the following theorem. Suppose R is a relation from A to B. Then, R is equal to R inverse inverse. Okay, before we get into the proof, I'd like to give a little bit of context. Given in general a relation J from C to D, J inverse is the set of all ordered pairs in J with the coordinates swapped. So really, we have that for all objects x and y, x comma y is an element of J if and only if y comma x is an element of J inverse. Right, and so we're going to use this fact to help us prove the theorem. Now to start off the proof, let's suppose we are already given a relation R from A to B. So our goal is to prove that R is equal to R inverse inverse. Now, since R is a relation from A to B, it follows that the inverse of R is a relation from B to A, and therefore the inverse of R is a relation from A to B, right? So whenever we take the inverse of a relation, it just swaps these two sets around. Right? This is another way of saying that both R and R inverse inverse are subsets of A times B. And the way that we're going to prove that these two sets are equal is by showing that for all elements P in A times B, P is an element of R if and only if P is an element of R inverse inverse. Right? That is a valid way to show that two sets are equal. So now, let's use this fact to prove that these two sets are equal. And to do that, give me an arbitrary element of A times B. I'll call it P. And the whole goal now is to prove that P is an element of R if and only if P is an element of R inverse inverse. Now, what does it mean for P to be an element of A times B? Well, it means that there is some element A in A and element B in B such that P is equal to the ordered pair A comma B. Now, we're going to establish a chain of if and only ifs to show that P is an element of R if and only if P is an element of R inverse inverse. To see how that comes together, check this out. We know that P is an element of R if and only if A comma B is an element of R, right? Because P is equal to A comma B. But by our first fact right here, we know that given J's relation from C to D, that this is true. Well, if we take the two sets C and D here to be A and B, and we take J here to be R, well, yeah, R is a relation from A to B. So, what this means is, for all objects x and y, x comma y is an element of R if and only if y comma x is an element of R inverse. So we can take x and y here to be A and B. So we have that A comma B is an element of R if and only if B comma A is an element of R inverse. And now we're just going to apply this first fact again. The only difference is we're going to take C to be B and D to be A. Well, in that situation, we know that R inverse is a relation from B to A. So we're going to take J to be R inverse. So that means that this statement is true, where we say for all objects x and y, x comma y is an element of R inverse if and only if y comma x is an element of R inverse inverse. So on that note, well, this statement works for all objects x and y. So we can take x to be B and y to be A. Therefore, B comma A is an element of R inverse if and only if A comma B is an element of R inverse inverse. But again, since P is equal to A comma B, this is true if and only if P is an element of R inverse inverse. So notice, we have established a chain of if and only ifs showing that P is an element of R if and only if P is an element of R inverse inverse. Since P was an arbitrary element of A times B, we have that for all elements P in A times B, P P is an element of R if and only if P is an element of R inverse. Therefore, by this method, we have proven that R is equal to R inverse. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.